my name is Isaac, and today we'll go dive through activity number 23, regularized linear regression. In this video, I'll build and explain a regularized linear regression model to predict house prices from three features: size, rooms, and age. Regularization is a technique that adds a small penalty on large weights so that a model doesn't memorize noise. I'll use L2 regularization rich, which gently shrinks coefficients towards zero, and improve generalization when features are on different scales or correlated. I'll walk you through the code line by line, then compare two runs with different values of the regularization strength, lambda regulation, and finish with conclusion. So now, let's begin. Now we'll take a deeper look into the example. First of all, we're going to import three libraries: numpy for numeric expression, pandas for reading and selecting data from the CSV, and matplotlib to plot our cost curve. Now we're going to upload data. We're going to use the data function that features in the prices function to read the CSV file into a table. As you can see, here's the path of the file in my computer. Then we have to extract the input features, size, rooms, age, and the target price as numpy arrays. Now we have to normalize the data. We have to compute the column-wise mean and the standard deviation, and normalize each feature so they are on a comparable scale. This makes gradient steps and stable and differ across features. So now I have the mean, STD, and the features normalized. Now we're going to add one column for the intercept term. Here we create a column of ones for the intercept term bias. Build the final design matrix x equal to 1, x equal 1, x2, x3. Ensure y is a column vector for consistent matrix math. Now we're going to initialize all model parameters to 0. Set learning rate, how big each step is, iteration how many steps, and the lambda degree of how strong the LT penalty is. As you can see, the learning rate is 0.01, iteration 1000, and the lambda regulation or regularization coefficient is going to be 10 right now. Now we're going to use the call the cost function with regularization. Here in the cost function with L2, it is the usual mean square error plus a penalty on all the weights except the intercept or theta 0. MCE part measures to feed the data, and the reg part discourages large coefficients. So you can see here we divide it into the MCE and the regularization part, and then we return the sum of both of them to have a better order between the functions. Now we're going to call a function called the gradient descent or the gradient descent loop. What's going to happen here? Here we're going to compute predictions and errors, update the intercept with no penalty, update the other weights with data term plus the L2 shrinkage term, and record the cost each iteration to check the learning is stable and converging. And then we're going to return the theta and the cost history, as mentioned for the gradient descent loop. Now we're going to train the model, or what's going to happen. We're going to train the model to obtain the learned theta and the cost curve. As you can see, here are the two variables named, and here's the gradient descent calling all the functions before. In this section, we're going to plot the cost history. A good run decreases and then flattens. We have the plot at the x, the y, the title, and show the plot. Here we're going to define a simple mean squared error function to report training error. Now we're going to evaluate the mean squared error on the training data, compute predictions of the training data, and print the MCE and the final parameters for the functions and the cost. Now that the model is trained, we can use it to predict the price of a new house. I created a numpy array called new house with the characteristics of the house: 100 square meters, 4 rooms, and 12 years old. Because our model was trained with normalized features, I applied the same normalization formula, subtracting the mean and dividing by the standard deviation. So this new data is scaled in the same way as the training data. Then I add a 1 in front of the features to represent the intercept term, exactly like we did when building X. Finally, I multiply this new input by the learning parameters theta using a dot product, which gives us the predicted price for this new house according to our model. And then we're going to print the predicted price for the new house. Now we're going to do a comparison of lambda regulation values. We're going to run A will be equal to 10, and we're also going to run B. So first of all, let's run for letter A. The lambda is equal to 10. This is a stronger regularization. The weight shrinks more, coefficients are smaller in magnitude, the cost curve is more smoother, and converges steadily. Training MC can be a bit higher because the model resists overfitting noise, and prediction for the sample house typically more conservative or less extreme. Now we're going to do run B with lambda equal to 0.1, which is a weaker regularization. As you can see, the graph changes. And here the weights can grow larger to fit training data more closely. The cost curve will still decreases, but the model is less constrained. Training MC is often lower with a lambda 10, but organization can be worse if the data are noisy. For taking a look into a conclusion, we'll look into a quick example into MATLAB of the same regularization linear regression. And as you can see, we have the cost function iterations, and here we have the different theta, and we have that training MC. Now we can take a look into conclusions. I implemented regularized linear regression or L2 rich with gradient descent, and adding the penalty to both the cost and the gradient, excluding the intercept. A normalized input trained the model, plotted the cost curve, computed MCE, and predicted a new house price, comparing lambda 10 versus lambda 0.1. The stronger regularization produced smaller coefficients and a steadier cost curve, while the weaker regularization gave a lower training MCE, but potentially poorer generalization. Thank you for watching, and I'll see you next time.